If you do it correctly, you'll get the same answer, of course, in either any way. I would say that the last thing that was said is the most obvious thing to do. The question asked first. Now, what has been done on the board a while ago is actually perhaps a clever thing to do. Find out the proper time first. Just find out whether among the observers involved was somebody present at both events. Of course, the particle was present at both events. So, whatever time the particle measures is the proper time. You calculate that first, then you can actually use time dilation for both of them. You don't really need to even find out the proper length divided by, or in the rod frame, the thing that was done, which is fine, actually correct. The length traversed is the proper length divided by the relative velocity. You can do that. You can also simply find out that time by just using time dilation between these two observers. The reason why you can use time dilation at all is one observer is present at both events. So that person measures, in this case a particle, measures proper time. So you can find that out and using time dilation figure everything out. Okay. That's one way. The other way, the last way is actually perhaps the most direct. And that has nothing to do with relativity apart from only one thing. This fellow who is on the ground or who is doing the observing, he did not say on the ground. Somebody fixed to the ground is sort of a default thing that we say for observers when we don't mention anybody. In the problem, a question was asked by several of you in a mail to me, which is, when I say find out the time with respect to whom? And the answer is very simple. The moment we state that there is a velocity of 0.5 c and minus 0.5 c, I've already stated that there has to be an observer concerned. Right? Without an observer, velocity will make no sense. So when I say 0.5 c, you should have asked with respect to whom there. Once you take that for granted, then you can't time measure by whom. Then unless otherwise mentioned, it's always that observer. Okay? So the question is a valid question. Because time measured are different for different fellows. So you might very well legitimately ask, when asked for time measured by whom? But you should have actually asked velocity measured by whom before that. So if you took that for granted, then you have no right to ask time measured by whom. You should have set the question at the very first line. Of course, when you say that the speed is 0.5 c, you always mean that there is an observer in the background who is doing the measuring. And when you specify nothing else and ask for time, it has to be with respect to that observer. Okay? And there, all you need is distance divided by the rate of separation, or rather in this case, rate of reduction of separation. When the particle hit the right end of the rod, how far away was the left end? That's the length of the rod, of course. Remember simultaneously, at the instant when the rod particle hit the right end of the rod, at the instant, how far was the left end? This question again depends on the observer. And right now, we are only sticking to the first observer. How far is it? It's the length of the rod that observer measures. Proper length is 10 centimeters, so you can easily calculate that the actual length is less. 10 into root over 1 minus 1/4. That is 10 root 3 by 2, that's 5 root 3 centimeters. That's how far away the other end is. Divide that by the speed. But which speed? In this case, actually, you could call it the rate of separation, or you could simply say it's geometry. This is 5 root 3 centimeters. This particle is moving at 0.5 c. The left end, which is what we are interested in, how fast is that moving? 0.5 c. So you could either say that the separation is closing at a rate of, so it's really reduction of separation, not really separation rate, at a rate of 0.5 c plus 0.5 c. This has nothing to do with relative velocities. This is not velocity observed by any observer of something. It is the rate at which the gap closes. Or you could simply say, suppose time t is taken. How far does this flow travel? 0.5 ct. How far does this flow travel? 0.5 ct. The sum of these two have to be the original length. This is geometry. Nothing other than two straight lines add up in length. Okay? So I would say the first answer is something you can get by simple class 8 level calculation. The only thing which is not class 8 about this is that the length is not 10 centimeters, it's contracted. That's a special relativity thing. Everything else is just class 8 calculation. Okay? Then you could actually find the time taken in the Rod's frame by the approach that was taken, yeah, which is find out the distance the particle traverses in the Rod's frame, and that of course is the proper length of the rod, divide by the velocity. This is really a velocity, the velocity which the particle has with respect to the rod, and you end up with the answer, 12.5 light seconds. Finally, you could even avoid time dilation altogether and find the time out in the particle frame by asking how long is the rod in the particle frame. Again, length contraction, but now length contraction between, to use the relative velocity between the rod and the particle for the length contraction factor, and then divide that by the velocity of the other end of the rod, which is just 0.5 c. So you don't need time dilation to answer any of these questions. Okay, that doesn't mean that using time dilation is bad. Using time dilation is perhaps better. You could actually find the proper time first, then find out these two times directly, without going through any of these separation or velocity or anything. You know the relative velocity between the three observers. At least you knew directly one velocity, the others you have to calculate, and then you can easily find out the times taken. There are other ways of doing it, by starting somewhere else. Okay. Most problems in relativity can be solved in multiple ways. Typically one of them would be easier than the others. But depending on your way of thinking, what seems to be easy to one may not seem to be easy to the other. Okay? And unless you are using a very convoluted way of thinking, no answer is bad, as long as the answer is correct. Okay? If you mix up time dilation factors, put the gamma in the wrong place and so on, then of course the answer is bad. If you do it consistently, it's fine. But here you have the advantage that you can use time dilation because there is an observer involved who is present at both events. Very often you will not be that lucky. Okay. Then the direct method. Direct method meaning time is velocity. Time essential is distance by velocity. You get to use that. Okay. Even this one was actually time equals distance by velocity. It's just that you calculate this distance and add them up to figure out what the original distance was. You can always fall back upon those. Okay? And finally, I would also urge you to do one thing. These are numerical values, right? 10 centimeters, 0.5 c, and so on. Whenever you meet a problem like this, especially if it is not too trivial, it's always a good idea to try that again without the numbers, but letters. Use L0, U1, U2. Okay? Or U1 and minus U2. You want them to be approaching each other. And then, what you can even do is modify this problem as a means of, say, calculating the formula for the relative velocity. There are many things you can discover out of this if you want to. Okay, there are different ways of arriving. The moment you have different ways of arriving at the result. For example, I could arrive at this result without using the relative velocity at all. Or, right, because without using the 0.8c. In fact, we didn't use 0.8c there. We said length. How much is the length? That's 10 centimeters or L0. How much is the time taken? Is L0 divided by the speed of the particle. For that you need the relative velocity, right? But then you could use time dilation to get there. For that you again need the relative velocity of the particles, but you need it in the 1 square root of 1 minus v square by c square factor. You need it in two different ways. Insisting that they give you the same result will allow you to figure out that it has to be 0.8c. So, if you did it without using the numbers, but just using u1, u2 or something, you should be able to figure out that the relative velocity formula is u1 plus u2 by 1 plus u1 u2 by v square. Plus, because is really u1 and minus u2 being put together. So, all I'm saying is the same problem can be thought of in many different ways and try to figure it out in as many different ways as you can. And you might find, and that way you understand what you're doing better. You should also understand why the different ways are giving you the same result. Okay? That is, you have to be clear about where you can use time dilation, where you can't. For example, if this problem had been something else, like two rods of proper lengths L1, L2, speeds u1 minus kv, cross each other. Okay? And now you find the time in the original frame. If I say, you should not ask which frame is the time being calculated. If I just say calculate the time, it has to be with respect to whoever was observing un minus v in the first place. Okay? Calculate the time in that frame. Calculate the time in the frame of the first rod. Calculate the time in the frame of the second rod. Now here, what do you mean when it crosses? Yeah.
So, but what exactly is crossing? Because for one observer...
So you have to decide what is crossing.
Because for one observer, what is crossing is not crossing to another observer.
It actually is. Crossing simply means A prime are together, that's the first event, and B prime are together, that's the second event. That always means crossing to everybody. There is no ambiguity there. One end of the rod touches the other end. That is a given event. That everybody agrees upon. You may not agree upon when it occurs. That's a different thing. But it does occur. Right? This is an event. And this is the other event. Its process moves all the way around. B and B2. So, B and B, if I label them in the same order, that is left to right for both, then B touching A prime is the first event. A touching B prime is the second event. That's unique. There is no ambiguity there. How long does that take? That of course will depend on the observer. Which one? It depends on whom you are talking about. It's not always 0.5c.
So the particle is measuring the improper length, right?
Yeah, suppose I am sitting here, I see a rod move by me, move away from me at 0.5c. Right? This rod, the particle is also coming towards me at 0.5c. I am only bothered about the rod right now. How long is the rod? The rod will be its proper length divided by a gamma, and in that gamma, what velocity should I use?
So the velocity seen by particle.
Why? If I am seeing the rod, why should I bother about the particle? You have to take it in stages. The question number one is, I see the rod. I see the particle.
Improper length is measured by the particle, right? So the
No, wait a minute. Improper length is measured by whoever is seeing the thing. I can't use my length measurement and the particle speed measurements. But I can't use the particle's length measurement and my speed measurement. When I am standing here, I am seeing the rod move, right? I am also seeing the particle come towards it, right? How long is the rod with respect to me? That length does not depend on the particle. If the particle had not even been in the picture, the rod would have been the same length. Why do I care what the particle does?
the question it's about the particle.
It's about the particle crossing the rod, right? There are three different questions there. First question is, what is the time it takes in my frame? For that I need length in my frame, velocities in my frame. Okay? When I then ask, what is the velocity part? What is the time taken in the particle's frame? There is length in the particle's frame, speed of the rod in the particle's frame. Then I ask, what is the time taken in the rod's frame? Is length in the rod's frame? Velocity of the particle in the rod's frame. The one important thing is whenever you're dealing with particle time and distance and velocities, you can get velocity by dividing time by distance or use it in other ways, but as long as you use one observer, I can't use that fellow's velocity measurements and my time measurements multiply them and get somebody else's distance measurements. Okay? That is one thing you have to be consistent about. Strictly speaking, there is really no confusion. The confusion really comes from the fact that we inherently assume that whatever time measurement I make, somebody else also makes that, and tend to confuse the issue. My time measurement times my velocity measurement is my displacement. End of story. As simple as that. The thing is really very simple. It's complicated when you mix up things.
So when I'm applying the time dilation formula, like proper time is particle frame and dilated time is rod frame. So there
Or even my frame, depending on which one you are using.
So let me say that I am trying to find out the rod frame, particle frame time, and I know the rod frame time.
Yeah, then the rod frame part, you know the rod frame time,
I know I want
and you want to find the particle frame time.
So rod frame time equal to gamma into particle time, as particle time is proper.
Yeah.
So the gamma that we will use there, the V that it will consider.
Is involved the velocity of the particle with respect to the rod. Okay, whatever you, or
That's not 0.5.
that's not 0.5, that's 0.8.
Okay.
There you have to be careful. You cannot just use somebody else's measurement and plug it in here. Okay, now let me begin today's class let me just state something at the very beginning, a result of an observation. Around, I'm very bad with dates, so I will not even try to put in the exact year in which this happened. But let's say year X, somebody was observing a quasar and saw a jet of matter come out of it. It's a very huge jet which comes out of a quasar from time to time. So it's a bunch of very rapidly moving charged particles. Okay? And in X plus 4 years, 4 years later, people from Earth observed this jet. So this was still here, the main quasar. The jet had spread a bit and moved this far. Okay? Now, from the Earth, you cannot see actual motion. What you see is transverse motion. Line of sight motion can't be seen, right? If you look at a star, if the star is moving right at you, you cannot see it moving, right? Okay, one of the first lessons you should learn is how to silence your phone. Okay, I'm not asking you to switch it off. By the way, that's a good thing. Did I? Actually, I did. Okay, now you are only seeing the transverse motion because when you are looking at the sky, you can't see something coming straight at you. You can measure the velocity by using Doppler effect, for example. But what you see here is motion perpendicular to the line of sight, right? That you can see. The things are separating from each other, and people already had a pretty good estimate of how far away this cluster, this quasar was. Quasar is a special kind of star, so let's not worry about what that is right now. And it's not really a star, and let's call it a cosmic object. And because you know this distance, you know the angle it has moved through, you actually can figure out how far it has moved. Right? It's just r into theta. And the observation told us that this was around 25 light years. This separation. Okay. So what are you saying here? What we are saying is the transverse velocity, commutator velocity is 25 light years over 4 years. That's 6.25 light times the speed of light. Now, you might of course say that you cannot see the actual motion, you can see only the transverse component. You should realize that that makes things worse. The actual velocity may be much larger, you are only seeing a component, right? So, this was one of the examples of what is called a superluminal velocity. Now, faced by these and the fact that I am going to discuss today, which is you cannot exceed the speed of light, apparently, at least we will make that more precise. You might say several things. You might say, the first thing you might say is relativity is wrong, which nobody does. At least nobody does at the beginning. That's not your first option. You might even say that the observation is wrong, but the angle measurement is very precise. So you might say, okay, I suspect the distance measurement. It might be that the quasar is not really as far away as we think it is. It's actually much closer. So that distance which I get by multiplying the distance to the quasar by the angle, that's coming out wrong. But you have to realize that for this to come out less than the speed of light, this is already more than 6 times the speed of light, right? To explain this away by saying that we got the distance to the quasar wrong, we will have to get the distance of the quasar overestimated by a factor of 6, more than 6 actually. That's highly unlikely. These measurements are not precise, but we know roughly how precise they are. They're roughly within 10%, which is pretty bad according to lab measurements. But this is not something you can control. You only are based on observations. So 10% is a very decent thing to get. A 10% error in the length cannot explain a factor of 6 mistake, right? So it does seem something is definitely going wrong here. Either relativity is going wrong, or somewhere something about the experiment is wrong. But before we explain what's happening there at all, let's try to understand why relativity says that nothing can move faster than the speed of light. And so we are going to pick this up from where we left off in the last class with Lorentz transformations and try to understand from there. So just bear that in mind. I'm not going to explain this away right now, but this should be at the back of the mind as something that needs explaining if at the end of what we discuss, we end up proving that things can't travel faster than speed of light according to relativity, although with some caveats, then this really should be something that bothers you. This is, in fact, not only this, there have been at least 8 to 10 observations of such superluminal velocities at least at the astronomical scale. Okay. This is not an isolated thing. But let's now forget about this for the time being and let's go back to why we can't travel faster than the speed of light. At least try to understand what that statement means. But before we even go there, we have to talk about a very basic principle of all of physics, all of science actually. It's such a basic principle that is very often not even mentioned. It's always assumed to be correct. Is it a relativistic principle? The answer is no. It's a principle in all of science. And causality may sound rather sophisticated, but this simply says that's it. If you claim that something is a cause, now the cause must be a real cause. Not because somebody thinks it's a cause of something, but if something is really causing something else, if event A causes event B, then event A has to occur before event B, or at best can happen simultaneously with event B. Okay? A cause cannot occur after the effect has happened. And by the way, this is not only important in relativity, this is extremely important in all branches of physics and has many verifiable and rather important consequences. You will later see the fact that, for example, absorption lines in optics of a particular shape, that really is due to causality. That is, even if you did not know the underlying mechanism precisely, causality would tell you that certain things have to be this way. If they are not that way, causality would be violated. Now, before we come to STR, let's talk about the Newtonian world. I said Newton, but actually Newton didn't bother too much about causality.
So you wrote the statement cause comes before effect. So like, can you make this precise in the sense like what do you mean by cause?
I don't know. No, I can't. Cause is something which causes something else. That's it. That's more. How much more precise do you want? Event A causes event B. Event A is the reason why event B occurs. Now you might say, I might want to say India wants to host the Olympics in 2036. Bad idea. But and therefore we build the stadium today. Okay. But the Olympics in 2036 is not the cause of building the stadium today. The decision that we are going to host the Olympics, if we are going to, in 2036 would be the reason why we are just building the stadium today. Okay. It's not 2036 Olympics which is the cause of this event. The stadium being built. Okay. So, in ordinary language, we often mix up cause and effect in many ways, like this example that I just gave you, which is still thankfully hypothetical. But given people with enough propaganda ideas, they might even want to do it, which usually is a disaster for every city which has hosted the Olympics so far. Not a great idea for our economy. But anyway, if somebody wants to do it and wants to build a stadium in anticipation. Now, in ordinary language, we might say hosting the Olympics is a cause for the thing to be built. That is not a cause. The cause is today I decide that I will host the Olympics, or I will even at least try to. And that's why I started building the stadium. That building of the stadium will come after the decision, will come before the hosting of the Olympics. So we often say Olympics would be the cause of this. Okay, for Olympics you substitute any sporting event which actually occurred, like say the Commonwealth Games or something. Somebody made a lot of money by say siphoning of funds for Commonwealth Games. Fine, but it was not the Commonwealth Games which was the cause. The siphoning of the money occurred because people put in money in trying to build the stadium, and somebody with not a lot of morals could take away the money. Okay, it is part of the money. They did build the stadiums. So the common sense use of the word, common language use of the word cause and effect is not what cause and effect means. And we will make that more precise exactly soon. Yeah, in the physics sense. That again is a wrong thing. Force causes acceleration is just a way of force and acceleration occur together. Now, which one causes which? We tend to think of force as being the cause of the acceleration. It's not really the force which causes the acceleration. It's the other particle present which causes the acceleration. So, say in Newtonian physics, you have a particle here, you have a particle there. There's a force between them. You move this particle, the force on this particle changes. That's an effect. In Newtonian physics, that would happen instantaneously. It's accelerated distance at the worst. Accelerated distance is there is always accelerated distance, right? These two things are distant, yet they cause a force among each other, right? So that's the accelerated distance. But here, when you move this, at that very instant, this particle's force changes. That's what the formula for the gravitational force would tell you. Relativity tells you that it cannot be correct. Okay, because instantaneous action cannot happen. We will come to all this. But moving this particle here is a cause. The force on this changing is an effect. Okay? Yeah.
So like you said, like force causes acceleration, which is apparently not true.
No, it's not apparently not true. Force causes acceleration is a common way of putting it.
Right.
Cause and effect is, I move this, force here changes. That's cause and effect.
So how do we decide? Like suppose we have two.
We will come to
How
that.
do we decide that which is actual?
Well, experiments, sometimes you don't, suppose you have two different possibilities and you change one of the possibilities. That's how you do controlled experiments, right?
So you change one.
You change one, keep the other intact, see whether the same thing happens and so on. That's basically the basis of all science. Now that, by the way, if we get into this, we will get into a debate about what science is and how science really occurs. And if any one of you wants to do this, there's a full philosophy of science course later on. Take it, because it's a complicated thing. Okay, for the time being, we are being simple-minded. We assume that we have a very, very strong physics version of what cause and effect is. We will come to that soon. But let's come to this Newton thing first. In the Newtonian world, you had an observer who measured x and t, and just to be consistent, let's use ct even in the Newtonian world. Of course, for slow-moving objects, if you use ct as a speed, as a time, the trouble is things will move way too slowly. So So most objects will almost not move vertically at all. That is, in any c delta t time, it will move such a long distance horizontally that the tracks will look almost horizontal. But anyway, be that as it may, this is here and now, which we usually call the origin of space-time, an event which is occurring at this instant at my location. So, in the Newtonian world, all of this above this axis is the future, all of this below is the past, and the idea is any event here could potentially be the cause of this event. Potential doesn't mean that everything that happens before is the cause of what happened here. But anything here can be the cause of this, can be in principle the cause of this, and this can be the cause of anything up here. Okay? Anything. Again, can be does not mean is. Okay? Something may very well happen after I start eating my breakfast. That doesn't mean that because I had my breakfast that thing happened. Okay? But in principle, all potential things that are caused by this must lie up here. All potential things that could be the cause of this must lie down here. There's one exception. Anything on this line, which is till now, any event here in the Newtonian world could be either the cause of the event here and now or the effect of that. Because in the Newtonian world, effects can travel instantaneously. So this is the Newtonian world, not the Einsteinian world that we are talking about. But Newtonian world essentially divides all events into essentially four classes. The future, which is just t greater than 0. I'm talking in respect to this particular event, which is at t equal to 0, x equal to 0. All t greater than 0 events constitute the future of this event. All t less than 0 constitute the past, which of course is simply what future and past means in the English language. Positive t is the future of t equal to 0. Negative t is the past of t equal to 0. So there's nothing very special about this. What is special is the cause and effect statement. That in principle, this event could be the cause of anything here. In principle, this event could be caused by anything here. Again, could be, doesn't have to be. Okay? But an event here cannot be caused by this event. That's absolutely certain. And the event here cannot be the cause of this event. Okay? That simply cause comes before effect. Okay? The only other class is all events other than this one on this line, which could be either the cause or the effect of this one. Could be, it doesn't have to, can't be both, but could be either cause or effect, or could simply not be cause. Okay? Yeah. Why not?
In Newtonian world or in
Newtonian world. This is the Newtonian world.
or in general?
What do you mean by in general?
In a
Newtonian world is perfectly general. Get the words right. Newtonian world is perfectly general. Well, is this the world that we live in? The answer is no. But our world is very closely, approximately Newtonian. And in our world, we do it. After all the calculations we do using the force of gravity or Coulomb's law, change this particle at the very instant the force here changes. That's cause and effect happening instantaneously. So simultaneously to moving the particle here, if event A was moving the particle, event B was the force changes, that's exactly simultaneous. In the Newtonian world. This does not happen in the real world, it takes a time delay, but that is not in Newtonian physics. Yeah.
So you said anything in the Newtonian world on that origin line can be the cause of
Origin line, or you mean the horizontal line?
x-axis.
On the x-axis, yeah.
X-axis can cause the event at the origin. If you have to.
Can cause, does not have to.
Yes. So can an event cause itself?
Well, no. Again, we are getting into philosophy. An event When you say cause and effect, you are always talking two different things. Cause and effect are two different things. Can it even cause itself? The answer is that's a trivial statement. An event causes itself trivially or does not cause itself again trivially.
Because we don't know associate that like.
No, but events, okay, by the way, let me just make this one point. You are actually right. Events don't mean what is happening. Events just mean X and T. So can the event 00 cause the event 00? In fact, it almost always does. Suppose I send a radio signal to a bomb, that's a violent example, but let's do that, and the bomb bursts. When does the bomb burst? When the radio signal reaches it. If that is 00 for some observer, then both events are 00. In fact, almost always every event causes itself. What happens at the event are two different things. Events in the physicist language are time and space points. Radio signal reaches 00. That's an event. Bomb bursts at 00. That's the same event as far as X and T is concerned.
So event and what is happening at the event
Are two different things. Events in the physicist language is just XT points. Okay. But when we say cause and effect, we actually mean the other sense.
Yes.
So, in that sense, of course, an event in the physicist sense causes an event in the physicist sense. Always, almost always. The signal has to get there before the thing happens.
So you said cause comes before effect. You also said that like the signal reaching and the bomb bursting are the same two events.
Or, okay, before is a sort of a oversimplification.
Before or and simultaneously.
Before or together. Never after. Cause never comes after effect is the correct statement to make. Okay. Cause comes before effect is usually what you say. Never comes after. Is the explicitly correct statement to make. Okay. Yeah.
So suppose we have two events P and P prime. P at x, comma T and P prime at x prime, comma T. And so
if T prime is less than T.
Yes sir, coming to that sir. So T prime is greater than T.
Okay.
So we say suppose say P is in now T prime will say happen in the future.
Yeah.
Is what we are saying.
Yeah.
But now by Newton's third law, say every action has an equal and opposite reaction.
So
say
that-
there is a body giving a force on another body and we are moving, coming to an example. Now after we have moved the body which has been moved also puts the force on the previous body. So wouldn't that mean
Why are you complicating things? Even the very fact that this body force changes at the very instant this moves, even that would require instantaneous transfer.
yes sir, but while this is moving, the body which moves also puts a force back on the
At the same time.
yeah, so wouldn't that mean by P and P prime the future influences the past?
Where did the future come from here?
Because we say that P is the cause of T prime.
First of all, if you believe in instantaneous transmission of forces, then T and T prime are equal.
So, but we say anything in T can cause.
Yeah, but the action and reaction are not cause and effect in the. That is one of the most simple mistakes which people make about action reaction. Action is not the cause and reaction the effect. That is one of the most rookie mistakes you make in mechanics. The first thing that you learn, and that's because our language uses action reaction in that way. Unfortunately, we borrow from physics without understanding that, and we say, okay, because you slapped somebody yesterday, he is coming and beating you up today. Or he has got his friends together to beat you up today. Okay, sorry for the violence in the example, but that's not action and reaction. And that's not physics action and reaction. In physics language, action and reaction would be when you slapped the fellow, your hand stung. That's action and reaction. Okay, in physics, action and reaction is simultaneous. In Newtonian physics. Okay? So, the kind of action reaction you're talking about, as being cause and effect, that's a standard language usage of the word, which has caused a lot of grief. When you couple it with the physicist version, every action has an equal and opposite reaction is one of the most abused language sentences in the English language, because it's used everywhere without any idea about what it really means. Okay? It sounds nice. Although people try to modify it and say every action has an equal but larger reaction and stuff like that. You break a chair, you get fined maybe 2,000 rupees. The reaction, of course, is bigger than the action. Yeah. Actually, less. The chairs cost more. But the point is that's not action and reaction in the phrases sense. Action and reaction, there would be when you broke the chair, you hurt your hand. That would be action and reaction. At least, approximately, if you understand what I mean. Now, let's come to this. We will soon get the answers to many of your questions anyway in the working. But let's just point out one thing. Was causality a feature of Newtonian physics? It definitely was. But nobody bothered talking about it. Why? No, because, okay, is causality correct or wrong? That's something you can decide by experiments. I am an observer, I see event A occur, I see event B as a cause of it. I can measure the times, I can always see TA to be less than or equal to TB. Okay? So T of the cause is less than or equal to T of the effect. Now, which one is the cause, which one is the effect between two events, if they are at all causally related to each other? Of course, two events may be completely causally unlinked, right? Not everything that happens afterwards has to be caused by this, right? So, but if two events are causally linked, if one actually causes the other, then we know that T cause must be less than or equal to T effect. Now, which one is the cause, which one is the effect? Is this observer dependent? Who looks at it? Does that decide which one is the cause, which one is the effect? No. So if A causes B, then A causes B for everybody. Should not be an issue. But that is all fine in Newtonian physics, because T cause less than equal to T effect is also observer independent. Right? In Newtonian physics, T cause is the same for all observers. Right? T effect is also same for all observers. Time for a given event is the same for everybody. Okay? Newtonian physics has this absolute time which is observer independent. What that means is, suppose I see, okay, let's not call them cause and effect, let's call them A and B, that's easy to write. I see A cause B, and I see TA less than equal to TB, causality is fine for me. Another observer who is moving is such to be, will the other observer also see A cause B? Because cause and effect does not depend on the observer. Will that person also see TA less than equal to TB?
Yes.
Yes? Right? Because whatever is TA for me is TA for him, whatever TB is for me is TB for him. End of story. What that means is, if causality is correct for one observer, it's correct for everybody. Whether it is correct for one observer or not should really be subject to experiments, but it's one of those proto-principles which people don't even question, although they do. They do lots of experiments to see whether this is right. But the important thing is, if it is right, it's right for everybody, no questions asked. Because Newtonian physics doesn't even allow you to ask this question. Clear?
Sir, in one thing, in Newtonian physics, this is because cause is instantaneously causes an effect.
No, I have nothing to do with it. Doesn't have to. Not every cause happens instantaneously, right? Suppose I have a flexible string and I pull one end. The other end may also come to me. But will it happen instantaneously? Of course not. Even if I pull this, will the other end come instantaneously? The answer is no. It will take some time for the signal to travel to the other end. Basically, the time it takes sound to move through this, or mechanical vibrations to move through this.
But then, for example, if the signal has to travel from one end to the other, right? For the effect to happen.
Yeah, so it takes time.
So, say if I travel faster than the signal.
Then what happens? Even then makes no difference. If you travel faster than the signal, the only thing you will say is that instead of the right end traveling back, you will see both ends are to the left and they will travel to the other side. Makes no difference here. The time taken is the same, no matter how you move. Now, this fact made causality a sort of trivial thing in classical physics. If it works for one observer, it works for everybody. Now, if you look at Einstein, or to be more precise, the Lorentz transformations, what do you have? Let's focus on this result, the time transformation between two observers. We are using the special Lorentz transformation simply because that's enough to get the idea across. Now what we are really interested in is a time interval between two events. So two events occur at times t1, t2, positions x1, x2. What is t2 minus t1? Delta t. But that's also easy to figure out because this is a linear transformation with constant coefficients. This is what we get. Okay. Now the 1 by square root of v square, 1 minus v square by c square may be the factor which looks the most important factor in this formula. After all, that's where time dilation etc. comes from. But we are really not bothered too much about that one right now. We are bothered more about this, that the numerator has this combination. Remember, in classical physics, that is, when I say classical I mean Newtonian. Unfortunately, the word classical means different things depending on where you are. Okay, when you're doing modern physics, then classical would mean STR is also classical physics. But in our class, classical means Einstein. In classical physics, delta t equals delta t prime. And because t equals t prime. So if I say delta t is positive, that is Tb minus Ta is positive, or non-negative, everybody will say it's non-negative. Here you see the issue. It's possible that delta t, Tb minus Ta, is positive and delta t prime is negative. Okay. Now, A causes B. Does that depend on whether the primed observer is looking at it or the unprimed observer is looking at it? No. But Tb greater than Ta, that might be a statement depending on the observer. So causality is at risk in special relativity. You get the issue. Time, not only is time not the same for all observers, even time order is not the same. Positive delta t, meaning Tb is more than Ta, might very well lead to negative delta t prime, where Tb is less than Ta. Tb prime is less than Ta prime. Okay? And so if we now say that A causes B, then it seems like for one observer, A is occurring B, causality is fine. A is occurring before B, causality is perfectly fine. But for the other observer, A is occurring after B. And now we are in deep trouble. Causality is violated. At least it works for one observer, does not work for another observer. Clear? So, causality means what? This? Or if delta t is Tb minus Ta, right? Now in Newtonian physics, delta t and delta t prime are the same. Simply because t and t prime are the same. And what does it tell you? It tells you that if one person agrees that A occurred before B, everybody agrees that A occurred before B. So if one person says A occurs before B and A causes B, causality is fine, everybody will have to say causality is fine. In Einsteinian physics, this is how time transforms. And now if you look at this formula, because of the presence of this term, it tells you that if delta t is maybe positive, that is Tb is more than Ta, so the original observer, I see A cause B and Ta is less than equal to, Tb is greater than equal to T. That is delta t is positive or non-negative to be more precise.
Then we may choose something else to be future in this system.
Yeah, but the point is, you made, so then your definition of future changes depending on who is observing. But A causes B, will that change? But then you see that A causes B is correct for me and Ta is less than equal to Tb, delta t is positive, I am happy with causality. somebody else sees TB is less than equal to T, because delta T prime works out to be negative from this formula. Causality will, now the point is cause and effect, does that change? If A causes B for me, for that fellow also A has to cause B. Right? Cause and effect does not even know who is looking at the thing. Right? But for that fellow, A still causes B, but A is occurring after B. So causality is violated. If causality is correct for me, it's wrong for him. Now causality is such a principle that you don't want it to be wrong for anybody. So that is where a problem lies with this.
Is in Einstein's physics, will there be equal sign? Is it not greater than equal sign?
It could also be equal, because after all the event could be right at the same x.
But Einstein said that
Delta x equal to 0 is possible. Right?
but information cannot travel inside.
Yeah, but radio signal reaches here is an event. Bomb goes off here is an event. Delta x equal to 0 is very much possible, right? So, which one is the cause, which one is the effect? Radio signal reaching is the cause, bomb going off is the effect. It's also a cause. But radio signal reaching here is also the cause. An event is almost never caused by a single other event. Everything that happens is caused by many things. Many things acting together, right? If I walk out of this room and trip on the doormat, it would be because somebody in the past kicked the doormat and made it curl up. It would also be because I was not paying attention. It would also be for some other reasons. It could be that I may have had a bit of bad news in the morning, so I was not thinking correctly. Many things contribute to a given event occurring. So all of them are causes. Okay. So just because radio signal reaching the bomb is a cause of the bomb going off doesn't mean that my sending the signal is not a cause. That could be a very bad defense to put up in a court. Right? You might say, okay, I didn't really cause it. The radio signal reaching the caused it. I'm pretty sure no judge would ever listen to that.
So the judge would listen to it, he just wouldn't clarify.
Ah, would listen. Great. That's a very good point.
That is cause and effect.
Yeah, exactly. Good. Thank you. Okay, now, the question is, how do we get out of this problem? This is a problem. If you want to keep causality intact, which we do. Now you might say, why do we want to keep causality intact? After all, why don't we give that up?
Change the region where we say.
It would basically, if you give up causality, then better not do science at all. Okay. Science is basically about cause and effect chains of things. If you really give up on causality, science would really collapse. Now that is a religious reason for wanting causality. Okay. It's really a matter of faith. Why do we actually believe in causality? Because we have not seen any example of causality violation in real life, in experiments. That's the real reason why we believe it. But I'm pretty sure that if tomorrow somebody saw causality violation, the first attempt would be to discredit that observation. Like, I'm going to explain why that would lead to causality violation soon. Then you should find some other explanation. You should not really say causality is being violated, at least not at the very outset. There are deeply ingrained principles which you give up only if you have an overwhelming amount of evidence against it. Okay?
Sir,
Yeah.
no, we got the formula by assuming causality holds, right?
No.
When we are drawing the graph, we the line.
We got the formula by as a T and T prime relation. Right?
Yes.
That should work no matter whether causality holds or not. We derived it using one particular way. Okay, there are many other ways of doing that. Okay? Yeah.
So, but the formula holds for V less than C, right?
The formula, by the way, the formula for V being more than C, that would be the velocity of the observer. Right? We will see. Okay, let's just hold on to that, with that. We will come to that. In fact, even for V more than C, this formula would simply tell you something, but let's come to that. There's something much more important than that. First of all, When will this apparent violation of causality occur? When delta t is positive and delta t prime is negative, right? Or you can also put it at the equal to 0 in one of the two, but let's not worry too much about that. Say positive delta t and negative delta t prime. That's a clear-cut sign of possibility of a violation. Can that happen? The answer is of course it can. The formula tells you that that's eminently possible. But now, the issue is if event A causes event B, then how does event A even cause event B? A signal has to travel from event A to the location of event B, telling this point that event A has occurred. Right? Unless some signal travels from the location of event A to the location of event B, there is no way to know that event A has ever occurred. Event A should not be able to modify anything at the other location. So there has to be some signal. I'm not saying what. Could be a radio signal, could be something else. But some information, something which carries information that event A has occurred, has to go from A to B. Okay? Now, hello. So I'm almost out of time, but I can't really take any questions right now because I'll finish this. I will take questions later. Next class. What do you know about the velocity of the information? The two events are occurring at two different t's, delta t time apart, delta x position apart. The signal has to get to event B when? Has to travel from A to B. But when does it have to get to B? For it to cause event B, when does it have to get there?
TV greater than T.
Either at the time of event B or could be even before. Right? A signal could, suppose a radio signal goes in, that sets into to the location of event B, that sets into motion several things that happen one after the other, and then finally something happens. So the signal could have gotten there before, not at that instant. But V info, what we know, has to traverse this distance delta x between the two events in time delta t or less. Either in time delta t so that when it appears at event B, at that instant event B occurs, or it could make it in smaller amount of time so it gets there before, gets to the location of event B before event B occurs, and after that explosion happens after certain things. So what you know is V info actually more than this. Either equal to delta x by delta t, in which case it gets to delta x, crosses delta x in time delta t,
Yes.
or more than that, so that it crosses delta x in time less than delta t. Delta t is just a time gap. No, delta t is whatever delta t was throughout. Time gap between event A and B. Delta x is the position gap. The position gap has to be covered by the signal in time delta t or less. So info velocity has to be greater than or equal to this. Right? Now, notice violation of causality will occur if this happens. Delta t is positive, delta t prime is negative. But what does that formula tell you? That will happen if d delta x by c square is greater than delta t. Right? Okay? Right, or that's just delta t prime negative if delta t is positive. Then d delta x by c square will be bigger than delta t, then that will happen. Or greater than c square. And delta x by delta t, what do you know about that? You know it's less than or equal to V info. Now this is where you have to be careful. When you are dealing with an inequality, you have to be careful about the signs. But this is pretty easy. You replace delta x by delta t. Instead of that, if you put in v info, it will only make this side larger, right? V into delta x by delta t already has to be bigger than c square. Replace delta x by delta t by v info, which is guaranteed to be more than delta x by delta t, or at worst equal to it. You are making it even worse. So this has to be the case. So the velocity at which the information travels from one point to another times the velocity of the observer has to exceed c square for causality to be violated. Okay. So if you have information traveling faster than the speed of light, remember that when you have a product of two things bigger than c square, the only way that can happen is if both of them are smaller than c or even equal to c, this will never happen. This can happen only if at least one of them is bigger than c, either v or v info. Okay, right? The product of two things cannot exceed the square of c unless at least one of them is larger. So how do you ban causality violation? You say that neither v nor v info should be faster than the speed of light. If they don't matter, you might even say that formula tells you that v is less than the speed of light because square root of 1 minus v square by c square and so on. But v info also has to be less than the speed of light, because if v info were more than the speed of light, you should be able to find a v which is less than the speed of light for which that formula works. And yet v times v info is more than c square, causality gets violated. Okay? Yeah.
Do example particles between particles?
No. Okay, no problem. Simultaneity is with the next class is preventing me from answering the question. The more interesting question is, why does that not violate causality? So we will take that up next day.